Hello everyone. Today we are going to learn about an important concept, a machine learning algorithm that is known as a support vector machines. So, what are actually support vector machines? Support vector machines are a powerful learning algorithm that are widely used for both linear as well as nonlinear classifications and regressions problems. And also, most importantly, we use the support vector machines to analyze outliers. So this is our support vector machine. Support vector machines, they are highly adaptable. So why we are using is because they are effective for various applications like text classification, image classification, spam detection, and anomaly detection, as well as gene expression analysis, handwriting identification, and many more. So SVMs are particularly effective because they focus on finding the maximum separating hyperplane. So what is this maximum separating hyperplane? We will be learning this as we move forward in our lecture. So it is a difference between the classes in the target feature, making them robust for both binary and multi-class classifications. In this outline, we will explore the support vector machine algorithm, its applications, and how effectively it handles both linear and nonlinear classification as well as regression and outlier detection. So, support vector machine basically is a supervised machine learning algorithm. So, SVMs, if we talk about SVMs, SVMs are basically supervised machine learning algorithm. So, what do we mean by supervised machine learning algorithm? We know that machine learning algorithms can be classified into two categories. One, we sell it as supervised, and another is the unsupervised machine learning. So supervised machine learning is those kind of problems where we have our features and the labels intact with them. So SVMs are particularly why we are using SVMs for all these tasks, because this SVM, they focus on finding the maximum separating hyperplane. So between different classes in the target feature. So this is what makes them robust for binary as well as multi-class classification. So in this, we will be exploring the support vector machines, its applications, and how it effectively handles both linear and nonlinear classification as well as regression and outlier detection tasks. So this is what I was talking about. That is, the SVM is a supervised machine learning algorithm. It can be applied to regression problems also. Now, SVM is best suited to identify the optimal hyperplane in an n-dimensional space that can effectively separate data points into different classes in the feature space. So this algorithm ensures that the margin between the closest points of different classes are known, which are known as the support vectors, that margin is maximized. So suppose here we can consider two independent variables, x1 and x2. These are the independent variables, and there is a dependent variable which are represented as either a blue circle or a red circle. So in this scenario, the hyperplane, which we define it, is a line because we are working with two features. So here, depending upon our number of independent variables, we generally make the use of the hyperplanes. Like for two features, the hyperplane will be a single straight line. For three features, it will be a plane. So there can be multiple lines on hyperplane. So if we can see, we see that this can be a potential hyperplane. This can also be a hyperplane. This can also be a hyperplane. So there can be three potential hyperplanes. But here our challenge is to determine the best hyperplane that maximizes the separation margin between the red and the blue circles. So this can also be a hyperplane if we see. So there are four possibilities of a hyperplane. But among them, which one to choose? Which one can best separate these two classes? If we see these are the two classes, then which one of them the best separating line for the two classes? So this is the main objective of the support vector machines. So this maximization should be, the margin should maximize the separation between this red and blue circles. So it is very clear that there are multiple lines from this figure. So how do we choose the best line? Okay, or what we can say is how we choose the best hyperplane. So these can be told as the hyperplanes. So how can we choose the best? That segregates our data points, right? So One of the reasonable choices, the best hyperplane we can choose in a support vector machine is that one I told that maximizes the separation between the two margins or two groups or two classes, right? So if we see now, there can be, we have chosen this three possible hyperplanes, right? So the maximum margin hyperplane, also we called this as a hard margin, is selected based on maximizing the distance between the hyperplane and the nearest data point on each side. So if we see here, we can see that for L1, the distance from this is to the blue line, blue dots is this much, and well as in L3, this is this much. But whereas if we consider as L2, the distance from here to the blue point is this much, as well as the distance from this is this much. So we can surely say from this picture that this L2 hyperplane maximizes the separation. This maximizes the separation margin, and we can choose as our optimal hyperplane, right? We can choose this L2 as our optimal hyperplane, correct? Now, moving on to the dimensions that I was talking about earlier. So the dimension of the hyperplane depends on the number of features. So this is very important. Dimension depends on the number of features. How? Like for instance, if there are two input features, the hyperplane is simply a line, right? As we can see in R2, that is the R2 dimension, if it is two-dimensional input features, then the R2, this hyperplane is simply a line. Whereas if there are three input features, the hyperplane becomes a 2D plane. So this is my 2D plane. And the hyperplane is basically a plane here, not a line. So as the number of features increases beyond 3, the complexity of visualizing the hyperplane will also naturally increase, right? Next, moving on, we will see that we are considering here another scenario. Like, so here we have one blue ball in the boundary of the red ball, right? Here we can see this is the boundary of the red ball, but suddenly here is a blue ball. So how does SVM classify this data? Correct? It's simple. So the blue ball in the boundary of the red ones, this is the outlier, right? So the SVM algorithm has characteristics to ignore the outlier and finds the best hyperplane that maximizes the margin. Okay, so again, we will fit a best hyperplane which will maximize the margin irrespective of this outlier. This is the blue circle that is lying in the boundary of the red ones, right? Because it is robust to outliers. So in this type of data point, what does SVM does is finds a maximum margin as done with the previous data sets we have seen. Along with that, it adds some penalty each time a point crosses the margin. So since this blue point has crossed its margin, so there is some penalty that is added here. And the margin in this type of cases are called the soft margins. So we call them as the soft margins here because we are adding some penalty. Okay. Yes. So what I was talking about is this one. So this is my hyperplane. So it ignores the outlier and finds the best hyperplane that maximizes the margin, right? As I explained in the above figure. SVM, what it is doing, it adds a penalty each time a point crosses the margin. So this type of cases, we call it as soft margins. Now, hinge loss is a commonly used penalty. So if no violations, no hinge loss. If violations are there, hinge loss is proportional to the distance of the violation. So what kind of violations means if it is violated, then we will apply a hinge loss which is proportional to the distance of the violation, how much it is getting violated, right? So right till now, we were talking about linearly separable data, like, but what about if the data are not linearly separable, right? So if the data are not linearly separable, like in this below picture, so we cannot separate it with a single hyperplane, as we can see. So what to do in this point of time? Okay, so we call a point xi on the line, and we create a new variable yi, okay, as a function of distance from the origin. So what we do is that this is what we do. So SVM will solve this kind of problem where it is not linearly separable, the data points, by creating a new variable which is called a kernel. Okay, so we will call point xi on the line and create a new variable yi as a function of distance from the origin O. So if we plot this, we get something the figure that is shown here. So in this case, the new variable that is y created is a function as a function of distance from the origin. It's a non-linear function that creates a new variable, and we call it as a kernel function. Okay. So next we come to the mathematical computations of SVM. So if we think of our problem as a binary classification problem where we have only two classes and we are labeling those classes as one as the positive one and another is a minus one or negative one. So we have a training data set, right, which will be consisting of input features vectors like x and their corresponding class labels y. So the equation of a linear hyperplane will be W transpose x plus b equals to 0. So this is the equation for a linear hyperplane separating the, as we have seen here. So there were some and this. So this is this hyperplane, both separating the two groups can be given by this equation. So here the vector W, what we have, it represents a normal vector to the hyperplane. That is the direction perpendicular to the hyperplane. And the parameter that we are considering here, B, it represents the offset or distance of the hyperplane from the origin along the normal vector W. Now the distance between a data point xi and the decision boundary that can also be calculated as by using this formula. That is the distance equals to W transpose xi plus b divided by Euclidean norm of W, right? So for linear SVM class, if we see this diagram properly demonstrates how we are generalizing the margin. So this blue and the green dots are basically showing two different classes, right? So these are the two different classes that we are seeing here. Now, this line, what we are seeing is W into X minus B equals to 0 if we go upper. And if we go this side, it is Wx minus B equals to minus. So 1 is 0. Okay. So this will be plus. W transpose X plus B equals to 1. This line represents 0. For label 1, W transpose X plus B is greater than 1. And for the label minus 1, it is less than, the W transpose B will be less than minus 1. So the distance of this gap in between the two classes, we write it as 2 divided by the norm of W. Okay, so we want to maximize this distance. This is our main motto. So nonlinear SVM can be used to classify data when it cannot be separated into two classes by a single straight line. I cannot separate them on a single straight line. Okay. So by using kernel functions, nonlinear SVMs can handle this non-linearity by non-linearly separable data. The original input is transformed by these kernel functions into higher dimensional feature space where the data points can be linearly separated, right? So a linear SVM is used to locate a nonlinear decision boundary in this modified space. So if we see here, what is happening? So this is the left side picture is showing a non-linearly separable data set. So SVM kernel is a function. This takes the low dimensional input space and transforms it into a higher dimensional space, right? So what it does is it converts the non-separable problems to separable problems. So here if we see, when we are passing it through the kernel function, somewhat we are getting a linear separability, right? Through this plane, right? So we can mark it as our decision surface or boundary, okay? So simply put, the kernel does some extremely complex data transformation. So if we see there, the data is getting here from here to here, it is getting transformed. And then it finds out the process to separate the data based on the labels or outputs that we have defined, correct? So here we can see how easily by moving through the kernel, we are getting this separability in the non-linearly separable data. Now, the function of kernel is to take data as input and transform it into the required form. So different SVM algorithms are used for these different types of kernel functions, and most popular type are linear, non-linear, polynomial, and radial basis functions and sigmoid functions. So these are some of the popular, okay? So if we see the linear kernel, so linear kernel, what it does is the same as a support vector classifier, okay? Or the hyperplane without any transformation at all. So it doesn't do any kind of transformations. It doesn't require any kind of transformations rather, okay? The polynomial kernel is capable of creating nonlinear polynomial decision boundaries. And the radial basis function, that is, we also call it as an RVF kernel, This is the most complex one, which is capable of transforming highly nonlinear feature spaces to the linear ones. It is also capable of creating elliptical decision boundaries, like what we say is enclosed decision boundaries. So these are the most famous kernel functions that are used in SVM algorithms to separate nonlinearly separable data points. So we will be moving on with this in our next video. Till then, we will here we have a clear perspective of how the SVM works on the linearly separable data set, right? So here we stop our video and we will continue this in our